satellite looks like it's roping out. Roar is audible again. I've never ever seen this before, ever. I've never seen anything like this. I've never seen that before.
Hi, I'm Skip Talbot. I've been chasing supercells and tornadoes since 2003. This is a video version of a presentation I put together for the 2015 DuPage Advanced Severe Storms Seminar and the 2015 Minnesota Severe Storms Conference on anticipating tornadoes using visual cues. As a storm chaser, this is information I found to be most specific to identifying when and where a tornado might form and what the current state of the storm is. Most of the photography you'll see is courtesy my chase partner, Brindley. We'll start with some supercell visualizations and how supercells are presented on radar. Then we'll do some structure identification using the radar as a guide. Next we'll try to identify what the storm is doing based on its visual appearance. Finally, we'll use some time-lapse video to do a full walkthrough of the life of a supercell with several tornadoes in between. A couple disclaimers here. The information in this presentation is going to be very specific to certain kinds of storms and tornadoes. It's by no means a complete storm spotting guide, and certainly not something on which your safety should depend. If you haven't done so already, attend a Weather Service spotting class. They're usually free and hugely informative. These classes are going to give you the foundation you need for identifying and understanding these storms. Finally, these storms are very, very dangerous. I'm going to stress safety here, but many of the features shown here were shot from dangerous positions. No photo, video, or tornado report is worth compromising your safety. If you're in the path of a tornado or tornado-producing storm, get to a safe shelter, preferably underground or in a reinforced safe room. If you're a mobile spotter, take an escape route that does not cross the tornado's path. I'm going to be focusing on supercells for this presentation because they produce the vast majority of violent tornadoes. Other storms produce tornadoes too, but we often don't have the characteristic structure and visual cues that we do on supercells. This is a schematic drawing of a classic supercell from a 1979 Lemon and Doswell paper. It shows the working processes of a supercell. The tornado forms at the occlusion of the rear flank and forward flank gust fronts. However, for spotters that aren't quite familiar with supercells or haven't seen many in the field, this may seem a bit abstract. So I'm going to be focusing more on real-world examples instead. This illustration shows a visual depiction of many of the parts of a supercell, and you've probably seen this in your spotter training. Unfortunately, you almost never see this presentation in the field. I say almost never because it does happen. Check out this amazing photograph from Chris Gullickson. He's captured the entire supercell storm here with a tornado ongoing underneath. Here are all the parts of the illustration labeled on the photograph. A couple are missing like the shelf cloud, and instead we have a beaver tail in its place. This is by far the exception when spotting storms. In the dozen or so years I have been chasing, I have never seen a scene quite like this. This is the reality of storm spotting. This is a tornado-worn supercell from about the same distance and angle as the previous photograph. There's so much haze and low clouds obstructing our view here that you really can't tell what's going on. You can just barely make out an updraft base here with an anvil stretching overhead. So we need other cues and points of reference to be effective spotters and get our bearings on the storm. Instead of a schematic diagram, I'm going to use some actual radar data as our map for where supercell structure occurs. This is what's called a classic hook echo. This is the supercell that produced the 2013 Moore EF5. It doesn't get any more textbook than this. We have a huge debris ball at the bottom of that hook too. As spotters, you should absolutely have radar data in the field. There's no reason not to have a smartphone anymore either. Get one and get one of these apps if you don't have one already. The two that are most valued by storm chasers are RadarScope and Pickle, spelled PYKL3. RadarScope is especially useful because it offers a high-resolution radar display that incorporates some of the Level 2 data. Pickle also has a host of features that are popular with spotters and chasers. If you're using a laptop or desktop at home, Gibson Ridge GR Level 3 and GR Level 2 are still the standards. Unfortunately, you need both of these programs to get the low and high-res radar. Our radar shows us two major components of the supercell. That's the forward flank downdraft on the top, the large lobe extending to the northeast. The other is the rear flank downdraft. The RFD includes the hook and the tornado. Here's a close-up of the hook. We're going to use just this part of the storm for reference because this is where everything of interest is happening. There's neat stuff like rain, hail, shelf clouds, and mammatus up in the forward flank, but almost everything related to the tornado is happening right down here. Here's the location and aerial coverage of our tornado for reference. The tornado is usually, not always, but usually in the southwest corner of the ball at the end of the hook. I should stress that all of the positioning and reference points are just guidelines. Storms do crazy stuff all the time that contradicts this. Let's do some structure identification, basically a trip to the storm spotting zoo. Supercells have all of these parts that have very descriptive labels, which I think are great for describing what they are and what they do. A couple of these you've probably never heard of before, like the horseshoe and ghost train. These are newer terms that storm chasers are kicking around that I think are also really descriptive. One of the first things I'm looking for as a chaser, and one of the most basic parts of the storm, is the updraft base, rain-free base, or just base. Warm moist inflow winds are feeding into and rising up to the bottom of this flat, mostly rain-free cloud base. That's our updraft base. The updraft winds go up at an angle from there and come back down as a rainy, cold downdraft that fans out along the ground. If you're in the rainy downdraft, your view might look something like this. You're straining to see the base through that rain. Also, if you're in the path of a tornado, your view may look similar to this as well. When our storm first pops, you'll often see a little green or yellow blip on the radar. At this point, the updraft base is usually skinny and elongated. The shaded orange area here depicts where the updraft base is relative to our radar blip. As your storm becomes more substantial, and if it's growing into a supercell, that updraft base often expands into a more rounded area on the southwest flank of the storm. What about when we have a hook echo with a tornado? The updraft base actually wraps around the hook. The RFD is essentially punching a hole through the updraft base and causing it to bow outwards, making this horseshoe-shaped updraft base. I found this horseshoe to be the most telling structure for getting my bearings on the storm and where the tornado is most likely going to be. Again, this is a rough guideline, but the tornado is usually at the top or north side of the horseshoe. We can see the horseshoe on the radar and in real life. We're looking north at the hook end of a supercell and a violent tornado. This is the Henryville, Indiana EF4 that occurred in March of 2012. There's our horseshoe-shaped updraft base and the tornado right at the top or north end where we'd expect it to be. Here are the basic wind components, just like the previous example, except we've got 2 downdrafts instead of 1. We now know, thanks to research from scientists studying these storms, that almost all of the wind feeding into the tornado is originating from the RFD. The RFD punches through the base here in this hole and feeds and drives the tornado. Our warm moist inflow heads towards the tornado as well, but actually goes up into the storm's base before it reaches the tornado. The forward flank downdraft off to the northeast feeds the wall cloud and also into the hook or RFD region. Here are the 2 parts that make up the horseshoe. You've got your updraft base and what's known as the RFD clear slot. The clear slot is the donut hole in the bottom of the storm. You'll hear chasers talk a lot about the clear slot. I can't always see it though, depending on my position, but I can often pick out that horseshoe shape, so I focus on that instead. Let's look at a bunch of examples here so you can get a feel for this structure. Looking north at a classic supercell with cone tornado. There's our horseshoe, tornado at the top right where it should be. But what if there is no tornado? If I can see that horseshoe, I've got a great idea of where it's most likely going to be if it does form. Indeed, we had an EF4 wedge form out of that location several minutes later. Much larger horseshoe here, but you can follow the rim of it around and our stovepipe is right at the top. Where's the horseshoe on this storm? This is kind of a trick question. There's actually 2 of them and they're difficult to see. We have a cyclical supercell with 2 tornadoes in progress. The older dying tornado on the left has a faint but visible horseshoe cut behind it. There's a more prominent horseshoe cut to the northeast where the new tornado is developing. Prominent horseshoe in the base of this storm, and I'd expect the tornado to be at the top up here. So why is there a funnel coming out of the bottom end? And the answer is it's an anticyclonic funnel, which may have developed into a weak anticyclonic tornado. What happens is our RFD curls in opposite directions as it fans out under the base, cyclonically on the northern end, where we usually get our tornado, and anticyclonically on the southern end. The anticyclonic circulation is typically smaller and weaker, and tornadoes are much less common here than on the cyclonic end. Spotters need to be watching out for this though. In fact, tornadoes are possible anywhere along this horseshoe-shaped feature, and adjacent parts such as inflow bands and flanking line convection. Spotters are often told to look for a strongly rotating wall cloud when anticipating tornadoes. I love this example because there's no wall cloud on this storm and we have a developing tornado coming right out of the updraft base. There's still a very prominent horseshoe though, and this is why I rely much more on this feature than wall clouds. Use the wall cloud as a landmark if it's there, but the horseshoe is often a better indicator as it's present more often and gives you better bearings on where things are located. Looking west at a high precipitation supercell, there's rain falling where we'd expect the rain-free base to be and where the RFD clear slot would be. Yet we can still trace out that horseshoe shape following the lip of the updraft base here. You can see the north end of the horseshoe curls back into the rain, and the spot where I'd expect the tornado to form is completely obscured. This is what makes spotting and chasing HP supercells so dangerous. That tornado is often completely rain-wrapped. Same storm, looking north now. Follow the lip of that base around to trace out that horseshoe. Again, the north end is completely obstructed by rain in the RFD. But if we have a visual on that horseshoe, we can infer where the tornado is most likely going to be. It doesn't get any more textbook perfect than this. This is the 2013 El Reno Supercell and Tornado extreme wide-angle view showing half the sky. You can see the Horseshoe updraft base is almost perfectly symmetrical. We have a 2.6 mile wide tornado in progress on the right and a developing anticyclonic tornado on the left. Here's a less conventional location you might find yourself in as a spotter. We're in the rain of the forward flank looking south. The top of the Horseshoe is closest to us from this side, and you can even see there's a nice curl at the end right where we'd expect the tornado. Again, for review, if you can pick out a hook on your radar, you can envision the updraft base wrapping around it like a horseshoe. Here's a visualization of our winds. The RFD on the left is feeding and driving the tornado. It curls in the opposite direction where our smaller anticyclonic tornado might be. The inflow feeds into the area of lower reflectivity north of the hook in an area we call the notch. And our forward flank downdraft at the top fans out in all directions and also feeds the hook region. Spiraling rain bands under the mesocyclone. What's the nickname for that? The bear's cage. That nickname is meant to sound scary, and it should, as this is the most dangerous part of the storm. It contains the tornado if there is one, and anywhere within this region can be impacted by tornadic winds without warning. The streaky bands of rain spiraling underneath the mesocyclone are the bars of the bear's cage. The tornado is the bear, often hiding in the rain within this region. This is the bear that was hiding in that storm, a photo from a few minutes earlier, a gigantic wedge tornado. You can see the streaky bands of rain marking the bear's cage region. Anyone who values their safety should not only avoid entering the bear's cage, but also stay out of its path. This entire region should be treated as if it is one large tornado. Here's what that looks like on our radar view. The bear's cage encompasses the entire ball at the end of the hook. That ball might be there whether there is a tornado or not, and that ball is often showing the rain falling through the RFD, those streaky bands that spiral around the mesocyclone. The tornado is often, but again not always, in the southwest corner of the cage. Looking southwest at a ground-scraping high precipitation supercell from within the notch. This greenish circular region under the base is the bear's cage. A closer look at what's going on underneath. We've got a cone tornado right here. There was a problem when Victor, Brindley, and I were watching this storm though. We were getting really intense inflow winds at our location, and we'd expect them to be heading toward the tornado, but they were heading to the left of the tornado. We realized the cone tornado was just a small satellite tornado. There was a much larger 1.5 mile wide EF3 hiding in the rain to the left. These satellites often form on the rim of the bear's cage, and there might be something much larger hiding inside, which is why it's so important to treat this whole region as one big tornado, as multiple satellites can form around that lip. The smaller circle here gives a better representation of the size of that satellite compared to the larger EF3. Looking south as I escape east from the bear's cage, on an HB supercell it's often a greenish circular region. As a chaser, I'm always looking for these streaky bands of rain that are moving from left to right under the meso. They're a precursor to tornado genesis, and I'm also taking my escape route to avoid them. There's an EF4 hiding in the rain to the right in this view. Looking west at the bear's cage, which fills the frame here in this view. We had a visual on a cone funnel in the distance, but the rain bands marking the edge of the bear's cage were careening at high speed from left to right. At this scale, that's what rotation looks like. Left to right motion, not a small twist. We realized that the entire bear's cage region here was becoming a tornado. Wide-angle view of the bear's cage on the 2013 El Reno storm. The bear's cage winds became so intense the entire 2.6 mile wide region became the tornado. Even this area of seemingly clear air to the left of the funnel was experiencing EF1 winds. This is why it's so absolutely crucial that you keep spacing from the bear's cage and have escape routes to take you out of its path. On this storm, I also think of this region more like a shark tank. The rain and winds inside make escape from this region very difficult, and there were several very fast-moving and intense vortices inside. Once you've fallen into this shark tank, it becomes a desperate struggle to get out, and you can very quickly get bitten. The turbulent wake behind the gust front is often called the whale's mouth. It's as if the storm has a giant mouth, and this is the view you see after you've been swallowed. What's happening here is the storm's outflow and gust front is acting like a little cold front. The warm moist inflow is being pushed up and over the gust front to form this cloud structure, and the underside often has this turbulent or roiling texture. This is usually game over if you're a chaser trying to find tornadoes. It looks dramatic, but it means the region producing tornadoes is cut off from that warm moist inflow. When I see this, it usually means a tornado is not imminent. But don't let your guard down. The storm can shed this gust front and reorganize. Before you're swallowed by the whale's mouth, you'll often see a big shelf cloud coming in from the west. You can see it on radar. It often appears as a blue or green line in front of the storms. When you see that line ahead of the storms, you can usually bet there's some sort of roll cloud, shelf cloud, or gust front headed your way. Heading toward the whale's mouth here. As a spotter, you're going to see something like this far more often than you will classic supercell structure. These gust fronts on storm complexes are very common. Swallowed by the whale's mouth here, you can often see these knobby or pointy lowerings on the edge of the gust front. This is scud and it's not tornadic. It's what I like to call whale's teeth. Plumes of dirt being kicked up by outflow and gustnadoes are common under this. The whale's teeth are stretched vertically by the updraft like taffy with outflow underneath. This fools many spotters. Dozens of tornado reports came in on this storm. They were almost all outflow and gustnadoes along the gust front. I see spotters making this mistake all the time when I'm chasing. You can avoid being duped by getting your bearings on other supercell structure and reading the storm's state, which we'll talk about a bit later. First, let's take a look at some beaver tails and other kinds of tail clouds. Here's a really pronounced beaver tail near Lincoln, Nebraska last May. These are features marking inflow into the storm's updraft. They're like conveyor belts of moisture being pulled into the base. And the base of the tail is often an indicator of where the updraft is working and a rough visual cue pointing to where our tornado might form. Here's a scuddy wall cloud, but it's got a nice tail cloud coming off of it, and that's what tells me that this is an inflow-based feature like a wall cloud and not scud or a shelf cloud. These tail clouds are feeding off the rain-cooled air from the forward flank downdraft. This cool, moist air condenses at a lower height, and that's what forms our lowering. Here's a huge wall cloud over the Denver airport. It's got a little nub tail cloud at the end, and again that's telling me this feature is drawing in inflow. The interaction with the forward flank downdraft is a lot more visible here. I'm using the base of this tail cloud as a focal point for getting my bearings on the storm and a rough guess as to where the storm might be getting ready to produce a tornado. It's not just tail clouds, there are all kinds of bands and inflow features that feed into the storm's updraft at different levels. We've got a band of cumulus in the mid-levels here that's being drawn into this supercell, and that's a real good indication of where that updraft is and that it might be strengthening. Tail clouds can come off the updraft base from any direction, but they're often coming off the top of our horseshoe, in the storm's inflow notch running along and into the forward flank, usually off to the northeast. Here's a term that I'd like to introduce to you guys. This is an important feature from a safety standpoint and not so much for getting your bearings or finding a tornado. There's a focus jet of inflow that feeds in from behind the tornado that's called the rear inflow jet. This is an extremely dangerous part of the storm. Several storm chasers I know have been injured by this or had their vehicles damaged. We've been kicking around a more descriptive name for this to convey what it is and how dangerous it is. This is a training line of gray mist moving along the ground at speeds of 100 miles an hour or more, sometimes just a few feet tall and wide. It's difficult to see and chasers are often fixated on the funnel when they're run over by this. Because of its motion and appearance, I like to call this the ghost train. You can see the ghost train moving through the trees in the foreground here and crossing the road up ahead. Here's that line of mist spiraling into and feeding a 1.5 mile wide EF4 in northeast Nebraska. The ghost train on this tornado took out a storm chaser's back window. Here's a really pronounced ghost train or inflow jet on the 2014 Tupelo, Mississippi EF3. The traffic here is scrambling to get out of the way of the funnel, but the ghost train is going to nail several of these cars, which could blow out the windows or bring the trees down. We're looking east immediately behind the 2011 Girard, Illinois EF3. The ghost train shows up well on the right. There's flying debris in that jet. In terms of the damage survey, this part of the storm is often considered part of the tornado, even though it extends out from the funnel and debris cloud. Here's where the ghost train is located on our radar scan. It's part of the rear flank downdraft in the hook, and is usually, but not always, located in the area behind or just to the right of the tornado, generally south or west of the tornado. It's possible for these inflow jets to come off the tornado at any angle though. Generally, you can avoid this feature just by staying out of the bear's cage and ahead of the rear flank gust front. Spotters who find themselves close to tornadoes, even if they're not in the path of the tornado, or immediately behind a tornado that is moving away, really need to watch out for this. There's a huge variety of shapes and sizes when it comes to supercells, but if we know what to look for, we can still pick out the visual cues. On this gnarly HP, our wall cloud and tail cloud is much larger and more robust looking than the rain-wrapped horseshoe. I'm using both of those features to gauge the tornado's likely location though. Small tornadoes are possible to the right under that tail feature as well. Visibility is often very difficult under HP supercells, so we want to use all the visual cues that we can to get our bearings. Infer the shape of that horseshoe under the updraft, and use those inflow bands to point the way. Same storm looking more closely under the base as it approaches. Lightning has backlit the structure underneath. There's a classic wall cloud with tail cloud right at the top of where we're trying to pick out that horseshoe. A cone tornado forms in this location about a minute later. visible through the rain only as the lightning illuminates it. Sometimes our visual cues are very subtle or rough looking, but if we're actively looking for them, they become much more apparent. Here's that storm a few minutes later with a developing tornado now. The updraft base, while scuddy and rough around the edges, is showing the characteristic visual cues as we look at the curling north end of that horseshoe and nub tail cloud. We can use these visual cues on all kinds of storms. Here's a big shelf cloud on a line of storms that's producing damaging straight line winds. Following the contour of the updraft base, we see instead of a horseshoe, it makes a linear line. And that's exactly what this storm is, a linear line, a mode we generally don't associate with significant tornadoes. Looking north at another shelf, these storms often look visually impressive, but without any of the visual cues associated with supercell structure, I'm not anticipating a tornado. Let's take a second look at this shelf cloud I showed earlier. It's actually got a tornado warning. But why? Tornadoes can be associated with lines of storms that are showing predominantly shelf cloud structure, including QLCS and mesovortex tornadoes, and supercells embedded within linear lines. This is part of a QLCS or quasi-linear convective system that's showing some low-level rotation and might be capable of producing a tornado. It's harder to pick out, but we do have visual cues on these storms that we can use to anticipate if and where a tornado might occur. It's subtle, but the top end of our horseshoe is visible here, even though this storm is showing mostly shelf cloud structure. Follow the lip of the updraft base around. It bows outward on the north end, and there is a noticeable kink in the line where the base is actually curling inward. This is the top or north end of the horseshoe. The kink in the line is also marking where the storm is drawing in warm, moist air from the surface. That kink is the inflow notch. I'm using the curl and the bowing gust front and the inflow notch kink as my visual cues for where a tornado might develop. It's a very similar pattern to the supercell structure we looked at earlier, but a bit more subtle. This is another great reason why you don't focus too much on shelf clouds or wall clouds, as we can still get a tornado even when looking at mostly shelf cloud. We can see this structure a bit better as the storm approaches and passes to the north. There's clearly a lowered area behind the gust front. That's where the north end of the horseshoe is curling. The kink marking the inflow notch is visible here too, but a little bit harder to make out. Like a tail cloud, it's roughly pointing toward where I expect the tornado to be. These are difficult and dangerous tornadoes to spot because they are often heavily rain-wrapped, like the tornadoes associated with an HP supercell. These features are visible on the radar, such as with this embedded tornadic supercell. QLCS, mesovortex, and embedded supercell tornadoes typically show some sort of hook-like feature, often identifiable as a bowing portion of the line, with a curl at the north end and a kink in the line north of there. If you can pick out that hook-like curl and inflow notch kink in the line, you can trace out the top end of that horseshoe and infer where that tornado might be, even if that area is heavily rain-wrapped. What's going on here? Is this a wall cloud or a small updraft base? Where is the horseshoe? The answer is, I don't know. Not every storm is going to present these characteristic visual cues. In fact, most won't, as the vast majority of storms are not supercells. Even some significant tornadoes can present themselves without these characteristic visual cues. For example, some of the more violent tornadoes will spin up before the horseshoe has had a chance to form. Spout tornadoes, including both waterspouts and landspouts, will present themselves without a horseshoe because they're not being driven by the rear flank downdraft of a mesocyclone. It's okay to not know what's going on. As a spotter, you want to report what you see, not what you think you see. In this case, I would report this feature as a non-rotating lowering. I really don't know much more than that. For safety's sake, you still want to give this feature and this storm the full amount of respect as you would a tornadic supercell. Even though we're not reporting it as such, treat an unknown lowering as if it's the bear's cage or a tornado, by not positioning underneath it and taking an escape route to stay out of its path. I don't know is a great thing because it keeps you safe. I don't know is your cue to get to shelter or take your escape route. Several storm spotters have been killed driving into storms because they didn't know what they were looking at or didn't have situational awareness. Let's take a look at several storm properties that I use to gauge the likelihood of a tornado, including whether our structure is inflow or outflow based, the storm is surface based or elevated, and some warning signs that a tornado is about to form and how strong it might be. This is a basic storm spotting rule of thumb, but it's a great one that I use all the time, and that's how to determine if our storm structure is being influenced by inflow or outflow. The rule of thumb is that the pointy end of our cloud lowering points away from the rain if it's an outflow driven feature, like this shelfy gust front here. And it points toward the rain if it's an inflow based feature like this scuddy wall cloud. It's a great rule of thumb because our tornado is usually going to originate from an inflow based portion of our supercell. Is this a shelf cloud or a wall cloud? The answer is it's both. Our rear flank downdraft usually causes the wall cloud to bow out into a big shelf cloud or gust front. As this is happening, we wind up with both elements blending into each other under the storm's base. The end on the left is being driven by outflow, like a shelf cloud, and the end on the right by inflow, like a wall cloud. And the other answer is that I really don't care if it's a shelf or a wall. What I've got here is a nice horseshoe-shaped updraft base that I can use to get my bearings on the supercell. And there's a nice tail cloud on the right indicating an inflow-based area. I have a pretty good idea of where that tornado is going to form if it does. Let's talk about whether our storm is surface-based or elevated. Here's our original diagram of the winds for reference. A storm with a shot at producing a tornado is pulling in warm, moist air from the surface. If we have unstable inflow originating at the surface, we call this storm surface-based, and visually the clouds above our storm will have a bubbly or cauliflower appearance. However, if instead our storm starts taking on these smooth laminar bands or bell shapes, I'm going to start to wonder if we're instead dealing with an elevated storm. This is an elevated supercell in western Kansas. They're amazingly photogenic and can produce large hail, but very rarely produce tornadoes. Here's the process of what's going on. Late at night or early in the morning, the layer of air near the ground cools off and becomes stable. The storm forms above this cool layer and starts drawing in its warm, moist inflow from a layer aloft, a layer elevated above the ground. That's why we call these storms elevated. Not that they're higher off the ground, but that they're feeding off of air that's higher off the ground. The updraft still pulls up this cool, stable air from near the ground, but instead of giving us that cauliflower shape, that's what forms these really cool looking laminar striations and bell shapes. Elevated storms are most common where the surface is cool and stable, such as overnight and in the morning, or on the cool side of a frontal boundary or outflow boundary. We can see these boundaries on radar, which often show up as little blue lines. If our storm is on the cool side of that boundary, generally west or north of the little blue line, our storm might be elevated, and its chances for producing a tornado are going to be diminished. Looking at this radar scan here, I would not expect a tornado to be imminent. Don't turn your back on that storm though. Here it is an hour later, and it's reorganized and it's actually ingested that boundary into the hook. If you see a hook pulling in that blue line or riding right on the top of it, watch out. It's tornado time. This produced an EF1 after dark. You can also guess based on the size and thickness of the hook here that we're dealing with a high precipitation supercell. In addition to the supercell structure we try to identify, there are several red flags that a tornado could be imminent. These are not guarantees. These are things that say, hey, pay attention, something might be going on here. The first are those streaky rain bands of the bear's cage that we talked about earlier. If I see streaky bands of rain moving rapidly from left to right, that's my first big red flag that this storm might be gearing up to produce a tornado. Because remember, rotation on that large scale looks like left to right motion. The next is a sudden surge in the inflow. It's like the storm is suddenly taking a really deep breath. The exhale might be the rear flank downdraft that kicks off a big tornado. Finally, sometimes before significant tornadoes form, there is a barrage of positively charged cloud-to-ground lightning. How do you tell the difference between negative and positive? Negatively charged lightning is far more common. There are those jagged and branching bolts. The thunder often sounds like a crackle, crackle, rumble, rumble. Positive bolts are at least 10 times stronger. The lightning channel is smooth and thick, not jagged and branching. The thunder often sounds like one giant and deep boom, like a mortar round. Here's a shot from the 2014 Pilger event. Sometimes there's a flurry of these strikes just before the tornado forms, and then the lightning goes silent or switches polarity. One of the most notable cases on which this occurred was the 1990 Plainfield F5. So we had these twin EF4 tornadoes we're watching in Nebraska last year. There's 2 of them already, so we don't have to look for any additional tornadoes, right? I noticed some positive CG activity, and the inflow was really starting to pick up. And I thought to myself, gee, that's odd. That activity usually precedes the tornado, but there's already 2 of them. Indeed, a third EF4 was forming right next to us, which we had to get out of the way of. We finally noticed the lowering well after we had been given several of these tornado red flags. The first thing I want to do for safety's sake is to determine which way the tornado is moving. I'm using the trees as a reference point and looking for left or right motion. There is no apparent motion here, and that means we are indeed within the tornado's path and need to act immediately on our escape route. This is it here a couple minutes later from a mile to the east as it passes extremely close to where we had been previously positioned. Remember that photograph of the cyclical supercell with 2 tornadoes? This video sequence here was a textbook example of how cyclical supercells spin up new tornadoes to the northeast, often while the older tornado is still in progress. There are some visual cues as to what kind of tornado you might be dealing with. If you start seeing several small vortices almost instantly condensing beneath the wall cloud or parent tornado cyclone, this is often an indication that this entire region is about to fill in as one huge tornado, what we call a wedge. What you're seeing are the subvortices of the tornado before the wedge has fully formed. When judging the intensity of the tornado, the size is often not the best indicator. There are some other visual cues we can use though. If you start seeing horizontal vortices and other funnels coming off the tornado at odd angles, this is a visual indication that you might have a violent tornado. These secondary vortices have been nicknamed vorticity noodles and indicate the presence of an extremely strong updraft and extremely strong wind shear. This is the Henryville, Indiana EF4. So let's put it all together and see the entire life cycle of a supercell storm. This is the May 22, 2010 Bowdle, South Dakota event. This is how your tornadic supercell begins its life, in a little patch of cumulus. There's already some towering cumulus starting to go up in the background. I sped the video up 16 times so that you can really see the motion. We'll let this entire event play out too so that you can get a feel for how these storms evolve. It's late afternoon and we're driving north. It looks like a really nice day, but there's a tornado watch in effect as the environment is primed for tornadoes. You can see the cauliflower look to the convection in those towering cumulus trying to go up in the background. This is the birth of our tornadic supercell. The updraft is so strong it's even creating a pileus cap above the tower where the air is being forced upwards. The growth of the updraft is explosive. Due to the hugely unstable atmosphere on this day, the storm goes off like a bomb. You can see the convection soaring thousands of feet into the air as I tilt the camera fully vertical. Tilting the camera back down, we have a visual on our updraft base, the first feature I'm looking for when getting my bearings on the storm. Here's our little blip on the radar that shows our fledgling storm. The updraft base is going to be elongated and skinny. In fact, there's actually several updraft bases within this orange shaded region. The storm has multiple updrafts at this point that haven't conglomerated into one yet. Heading north now to keep up with the fledgling storm, you can see several of those updraft bases. Looking to the southwest, there are several other towers attempting to go up. This is what we call flanking line convection. On a normal day, these towers result in a line of storms or storm complex. However, when the shear is favorable for supercells, these towers get aggregated into one supercell updraft. This developing supercell will eventually pull in these updrafts, consuming them and adding to its own strength. Precipitation is just starting to fall to the northeast as our forward flank downdraft develops. Looking back at our updraft base, you can actually see some broad left to right motion. This is low-level rotation in the updraft base. Even though this storm is still very much maturing, this is what I would call a low precipitation supercell. Look at what's starting to take shape underneath the updraft base. That's our characteristic horseshoe-shaped updraft as the rear flank downdraft first appears. The storm has just picked up a tornado warning now too, as the rotation is showing up on radar and this cell is moving into an extremely volatile environment. There's even a nub lowering where we'd expect the tornado to develop. I think this is a real half-assed attempt at tornado genesis. The rear flank downdraft probably hasn't developed enough to get this feature spinning into an actual tornado though. Again, for reference, there's our horseshoe-shaped updraft base. Our storm is looking much more robust on the radar. We're starting to get a little appendage there on the southern end there. That's the start of a hook echo. You can envision the horseshoe-shaped updraft base wrapping around that little nub on the southwest flank of the storm. That horseshoe is going to bow outwards as the storm sheds the gust front and gets ready to cycle again. Looking to the northeast now, you can see a tail cloud starting to take shape. This is the storm feeding off rain-cooled air from the forward flank as a wall cloud begins to develop under the updraft base and our storm cycles again. Watch how this feature expands as the storm pulls in that rain-cooled air. This storm has matured into a classic supercell, as we're now seeing some heavy precipitation in the forward flank, yet still have good visibility in the rear flank. We're moving east to stay ahead of the storm. As we turn north, you'll start to see the second cycle of the supercell taking shape with a faint horseshoe-shaped cut under the updraft base. Here's the horseshoe drawn on top of the video for reference. We had a really robust looking tail cloud now too, with all these little points underneath. Those points are marking circulations or areas of rotation, what we call vorticity, forming along the interface between the inflow and forward flank downdraft. The inflow actually pulls in these little circulations and they get aggregated into a larger area of rotation under the north end of our horseshoe. That's then stretched vertically by the updraft to increase the speed of that spin. This is one of the processes by which tornadoes form. Driving north here as we approach the base of this rotating wall cloud. There it is, the curl at the top of our horseshoe updraft base, with a thick tail cloud feeding right into it. At this point I thought for sure we were going to get a nice tornado. However, the storm still wasn't ready to produce and would cycle again a couple more times. Here's the radar at this time. We now have a classic hook echo. I've labeled the curl at the top of the hook where I'm watching for a tornado, the tail cloud extending off the horseshoe to the northeast from there. I didn't use the radar much at all on this chase. We had such good visuals on the structure that we really didn't need it. You should always trust your eyes over the radar, since the radar data is coarse, scanning a height well above the ground, and often significantly delayed. Because of these limitations, it's especially important that you not rely on the radar for your safety. If you lose your visual bearings on the storm, take your escape route. You can see a lot of churning motion and rotation here. There's downward motion on the back edge where our rear flank downdraft is working too. Looking north at the updraft base as we begin to move east. Watch how a surge in the rear flank downdraft causes that base to bow into a big horseshoe. The storm is cycling again. Here's that clear slot from which our RFD is causing the updraft base to bow outwards. And again the tail cloud feeding in on the right. Unfortunately, we had just one road to work with at this point, and it led directly under the base of the storm. We're going to drive underneath the updraft base and into the bear's cage in this next sequence. This is an extremely dangerous maneuver, and I can't stress enough that you should avoid doing this if you value your safety. Heading north now, you can see the rain in the rear flank downdraft wrapping around the curl at the top of the horseshoe. This is the bear's cage, and those are the streaky bands of rain that I'm always watching out for that precede tornado genesis. Watch the low-level rotation as we drive directly under this feature and encounter those rain bands. Luckily, there was no tornado at this time. We're driving across the bear's cage and into the hook of the storm now. This is an area where you may encounter severe winds and large hail in addition to the tornado. Not only is this a dangerous location, but it's a poor spotting location as well, since we're too close to identify the supercell structure we need to get our bearings. That's some sort of roll cloud under the base, probably forming along a forward flank gust front. We're heading north of the bear's cage into the inflow notch. Looking over my right shoulder back toward the bear's cage that we just drove through, there's some sort of suspicious lowering underneath the base. That's right where I'm watching for a developing tornado. The clear area to the right is where the rear flank downdraft is working to feed right into this region. Here's the radar now showing a ball at the end of the hook and our position from within the notch. Again, that ball is indicating where the bear's cage region is and marking those spiraling rain bands, circled in green here. As we turn east here to stay within the notch, watch as a wall cloud with a pronounced tail cloud forms overhead. That tail cloud is saying, "Hey, look over to the right." And there's our first tornado. A cone deep within the bear's cage region. Watch the motion of this tornado. It looks like it's orbiting the bear's cage, almost like you'd expect of a satellite tornado. There was another funnel behind it and orbiting the rim of this region. That's a big red flag to me that there's something bigger going on here than just these tornadoes. Our position at this time immediately northeast of the bear's cage, looking south. We realized we're in the path of this region at this time and we're going to take our escape route east, the quickest way out of the path. Just as we do so, another tornado almost instantly condenses and pivots around the bear's cage, almost like a subvortex. We clear this region as it crosses the highway behind us. Multiple vortices are now kicking up underneath, as this entire region has now become one large tornado, what I suspect is a developing wedge. Indeed, this is the start of the Bowdle, South Dakota EF4, which was over a mile in diameter. Our radar shows a textbook hook echo, and you can see we are positioned immediately east of the bear's cage and developing tornado located in the ball at the end of the hook. Watch the motion above that tornado as we pull away from it here. The RFD clear slot is wrapping around the tornado cyclone. Turning north, you can see the winds whipping around underneath as the tornado reorganizes. Heading through the town of Bowdle, you can make out the violent rotation and motion in the peripheral clouds above the tornado, and the tornado cyclone. This is something to watch for if your view of the horizon is blocked. A violent tornado is now well in progress. I love this shot because you can see the RFD actually wraps completely around the tornado, carving it out from the updraft base. There's this crevice that lets you look thousands of feet into the storm's blue-green heart. As we positioned in front of this tornado, we realized it was now moving more easterly than northeast. So we're in the path and need to take our escape route. Before we do, I want to point out this feature just to the south of the tornado. It looks like a benign area of clear air, but this is actually a really dangerous part of the supercell. This clear spot is where our rear flank downdraft originates from, and this area can contain large hail and damaging straight-line winds. Watch this area as it completely fills in with rain and wind a few minutes later when the supercell transitions into a high precipitation state. I also want to point out some really dangerous positioning we noted at this time. Storm chasers elect to take varying levels of risk, and I've certainly done my fair share of dangerous maneuvers. But all spotters and chasers should be aware of the potentially deadly consequences of operating inside the path of a tornado. In this case, storm chasers are using the unpaved roads to maintain a position in the path and immediately ahead of a violent tornado. These roads have a tendency to flood or can become blocked with debris or downed trees, cutting off the chaser or spotter from their only escape route. That's why it's so critical that you take your escape route as soon as you recognize that you're in the path of a tornado or tornado-producing region such as the Bear's Cage. Here's another chaser that's turning east onto the unpaved road grid to track this violent tornado from within its path. The conditions of that road up ahead are unknown. Worst of all, there might not be any road up ahead. That's exactly what happened on this storm. A group of storm chasers was using the unpaved road grid to maintain a position immediately ahead of the Bear's Cage region. There was an error on their maps, and their road suddenly disappeared, which was their only escape route. Fortunately, the Bowdle EF4 had since dissipated, and they missed impacts from several smaller tornadoes that passed nearby. This situation could have been avoided by maintaining multiple escape routes with known conditions and not holding a position within the path of a tornado-producing region. Heading south to get out of the way of this tornado, you can see the EF4 churning away at peak size and intensity. We had some car trouble and wanted to clear the RFD as well, so we continued on our south escape route back to the paved highway. Watch as that previously clear area completely fills in with rain. The tornado is now completely rain-wrapped as the storm transitions into a high precipitation state. It's far from done producing tornadoes though. We're moving east to get ahead of the storm. This is a cyclical supercell. You can see the updraft base redeveloping to the northeast. There's another big horseshoe cut developing in the base. We have a prominent tail cloud pointing right at the north end of it, and there's even a suspicious lowering right where all of this is coming together. I'm going to be watching that area closely for the next tornado. Moving east to get ahead of the rain as the supercell ingests a smaller cell moving up from the south. You can see some of the striations in the updraft base here. I'm still watching that same spot for a tornado. There's our funnel, and a trunk-shaped tornado quickly develops. A truncated funnel with subvortices spinning around underneath. Look at that inflow band on the right. That's a conveyor belt of moisture being drawn into the storm's updraft. There's a lot of motion under that base, and there's still probably a tornadic circulation in progress at ground level. This region soon quickly fills in with rain as the storm transitions back into a high precipitation state. The tornado is probably ongoing, but we no longer have any visibility on it. This supercell was remarkable for its ability to transition several times between a classic and high precipitation state due to the multiple dry and wet RFD surges that occurred. Most often, once a supercell transitions into a high precipitation state, it stays that way, as that rainy cold downdraft often causes the storm to gust out into an outflow dominant state. Here's some classic mothership type supercell structure. You can see the broad left to right motion in the updraft tower, indicating the mid-level rotation of the mesocyclone. We're going to head back down to that east highway to stay ahead of this storm. Given the supercell's history of producing violent tornadoes, we don't want to stay in the path of the Bear's Cage region or chance the conditions of the unpaved road grid. This storm goes on to produce several more small tornadoes, but many of them are heavily rain-wrapped as the storm has now permanently transitioned into a high precipitation state. We're also going to start losing our visual bearings on the storm as the structure begins to deteriorate. You can see that there are now multiple tail clouds forming underneath the base of the storm. Our flanking line convection has now erupted into a line of additional storms. This tornadic supercell is now embedded within this storm complex, and that's where it will eventually die as it gets absorbed. And that's the entire life cycle of a tornadic supercell. Thanks for watching. Don't hesitate to email me if you have any questions. Thanks again to Brinley for letting me use her photography for this presentation, and everyone else who contributed content. You're welcome to use this video for non-commercial and educational purposes.